Talk about what we know and also what we don't know about the relationship between climate and extreme weather. The heart of the problem, I think, is best illustrated by this little pie chart, which shows the composition of our atmosphere. As you're probably aware, almost all of the atmosphere is made of molecular nitrogen and oxygen. And the rest of it is made out of water vapor, carbon dioxide, and other greenhouse gases. That's the orange sliver. Our greenhouse effect depends upon a very tiny fraction of gases in our planet. So the difference between minus 18 degrees C, a frozen snowball, and our habitable planet is made possible by that little sliver. Carbon dioxide concentrations were pretty stable, around 280 parts per million, going all the way back to near the end of the last ice age. But beginning at the dawn of the industrial era, they've started to increase much more rapidly with time. And in fact, this year, they're exceeding 400 parts per million. So they're well on track to double or even triple, perhaps more. And that's the source of the concern. But by and large, the temperature has followed up the CO2 curve. There is not any real dispute in my field about this connection between carbon dioxide and climate. Where is the excess energy actually going? By far the majority of heat, as predicted theoretically, goes into the oceans, not into the atmosphere. Exchange of heat between the atmosphere and ocean is an important part of the internal variability of the climate system. This is what happens more or less when we have El Nino. What you see on this graph is the number of doublings of carbon dioxide. Theoretically, temperature should go up more or less linearly with that measure. And the straight line fit to that gives about 3 degrees of warming for a doubling right in the middle of the IPCC range. So what we understand about the global response to carbon dioxide is more than 100 years old and not principally based upon big complicated models. And on this graph is the radiative forcing change due to changing greenhouse gas concentrations and feedbacks associated with them. These different curves are for different projections that basically have to do with what we do. Are we going to stop emissions? Are we going to slow them down? Are we just going to continue with business? Nobody can predict human behavior, so we have to rely on a bunch of different kinds of estimates. So if we go business as usual, we're going to go up much higher in temperature than if we try to curtail emissions. How do you make decisions in the face of uncertainty? The same way you do with any sort of risk problem. You begin with a probability distribution of the event risk itself. So this is sort of our best shot at the global mean surface temperature change you would get from doubling CO2. We're on track to do much more than double CO2, but this is for a doubling. So the most probable outcome has a temperature change by the end of the century. It would be on the order of just shy of 3 degrees. When you assess risk, of course, you have to convolve this distribution with some estimate of how expensive to you, to your livelihood economically or to your life socially, the outcome will be. But if we go out here to 4 degrees or more, the consequences can be devastating. And when you get out into this tail, they might even be existential challenges. So this is the problem, okay, that we face, is that there is a very risky tail to this distribution, a very expensive, risky tail. And so the problem for society is, how do you want to deal with that sort of risk? Depending upon which projection you want to follow, business as usual or something else, carbon dioxide concentrations, even in this century, will probably much more than double. So if we don't do anything at all, we're going to cross that line before mid-century. And by the end of the century, we'll have more than tripled the carbon dioxide concentration in the atmosphere. That tripling really is going into very, very risky territory. Everyone that I talk to believes that. We're taking a real gamble with future generations if we go down that road. The other problem with this is that you can't, for scientific reasons, afford to wait very much. And the reason that you can't afford to wait is that once you put carbon in the atmosphere, it takes a long time for it to go away. Once you shut off emissions, there's an initial fast decay of CO2, but it literally takes thousands and thousands of years for it to go back to normal, all right? And CO2 has a very long life in the atmosphere. If we go up to 850 or 1,200 parts per million, we're stuck with that value for thousands and thousands of years. It doesn't just go back to normal in a few years. If it did, we could afford to wait. So we're going to now transition to a discussion of extreme weather. When it comes down to human or societal consequences of global warming, you start seeing temperatures you never saw before, and the really hot temperatures occur much more frequently. Conversely, the really cold temperatures occur far less frequently. This blue line here was the sort of Earth's mean surface temperature at the time of the big heat wave that killed 60,000 people in Europe in 2003. And the point is that that kind of heat becomes much more common as you go forward in time, because people adapt to heat up to a point. There is, unfortunately, in the issue of temperature, an actual upper bound or tolerance of the human body to heat that you can't go beyond. And that's not pertaining to temperature itself, but a quantity called the wet bulb temperature, which is a function of both the temperature and humidity. We have an absolute upper bound of 35 degrees centigrade in wet bulb temperature. If you go outside completely naked and it's 35 degrees centigrade wet bulb temperature, where you will actually die after a while. Your body can't get rid of heat fast enough. If you've been in a sauna, it's like that, and you can stand it for a little while, but you've got to get out after a while. Now, one thing that we are quite confident about is that hydrological extremes get more extreme when you warm the climate. That is, places that are already wet get wetter, places that are already dry get drier, and in general, rain is concentrated into fewer but more extreme events. So one expects to see, and in fact one is beginning to see, increased incidence of both floods, blizzards, and drought. Drought is perhaps one of the big issues we worry about when we ultimately worry about consequences for climate change for us. Insurance companies are very worried about this kind of phenomenon. I mentioned hail and tornadoes, and this is a map showing basically the places where thermodynamically you can have hurricanes, the deep tropics for the most part. And we know that as you warm the climate, that thermodynamic speed limit goes up, and it goes up appreciably. What we don't really understand is the issue of hurricane frequency. And in fact, most of us believe that global warming will actually reduce that frequency. So there's a strong relationship, as the thermodynamic theory basically suggests there should be, between the sea surface temperature of the tropical Atlantic during hurricane season and basically the energy of hurricanes. And that's one of the big worries we have from climate change, is that every technique we've applied and just plain old basic physics tells you that rainfall should go up rather fast as you, from tropical cyclones, should go up rather fast as you increase the temperature. We couple these hurricane models to storm surge models. Storm surges are usually the most destructive aspect of hurricanes. That's what happened in Sandy, for example, in New York. Katrina in New Orleans. It was a storm surge, by the way, is the same phenomenon as a tsunami hydrodynamically, except it's excited by wind rather than an earthquake, but it behaves the same way. So we would have estimated that a surge of Sandy's character was about a 1 in 700 year event. But if the climate isn't changing, and it may not be changing in a way that affects hurricanes in New York, then we were witness to a very rare event when we saw Sandy. A surge that might happen every few thousand years in the current climate happens, every 200 years or so in a future climate. So that's a really big increase in surge risk, although the amount of increase varies from one projection to the next. So there's uncertainty there.